Assalamualaikum and good afternoon to our fellow lecturer. We are from Group 2 and today we'll be presenting our assignment for groundwater control and dewatering system. In this presentation, we will explain the importance of groundwater control during deep excavation works. We will also discuss two case studies which are Merdeka 118 and Tun Razak Exchange TRX infrastructures before comparing the groundwater control methods used in both projects. Without further ado, let's begin our presentation. So, before we start, let me briefly introduce our group members. Our team consists of 5 members. First one is Aiman Haziq bin Shu'ib, Muhammad Anif bin Hazmizam, Muhammad Atif Najmuddin bin Mat Taeh, Muhammad Amirul Hakim bin Muhammad Rafi, and myself, Ahmad Ishraf Haikal bin Muhammad Nazim. Throughout this presentation, each member will present different sections of the report, and I'll be the one who will be presenting chapter 5, which is the comparative analysis. Now I would like to invite our first presenter to begin the presentation.
Our first case study is Merdeka 118, one of the most iconic construction projects in Malaysia. Throughout this section, we will be discussing the groundwater control measures and dewatering system that contribute to the successful completion of its deep basement excavation. Now, let us focus on one of the most iconic construction projects in Malaysia and currently the second tallest building in the world. This project involved a deep basement excavation in a densely developed urban area. One of the biggest engineering challenges was managing groundwater during excavation to ensure the stability of the foundation while protecting nearby buildings, roads, and underground utilities. In this presentation, we will explain the project background, the groundwater challenges encountered, the dewatering and the groundwater control method implemented, as well as the monitoring system and the overall effectiveness of this engineering solution. Let's begin with the project background of Merdeka 118. Before the basement excavation began, a detailed site investigation was carried out to understand the ground and groundwater condition. The project is located in Kuala Lumpur City Centre, which is densely developed urban area surrounded by existing buildings, public roads and underground utility network. Therefore, any ground movement or groundwater related issue could directly affect the surrounding infrastructure. The site consists of variable soil deposit over weathered rock formation and has a naturally high groundwater table. Since the basement excavation extended below the groundwater level, groundwater continues flow into the excavation area. In addition, Kuala Lumpur experiences heavy rainfall throughout the year, which further increases groundwater recharge and makes groundwater control even more challenging. Therefore, the engineering priority was to maintain excavation stability, control groundwater ingress and protect nearby structures throughout the construction process. Furthermore, I will discuss the main groundwater problems encountered during the excavation works. Merdeka 118 is a landmark mixed-use development located in Kuala Lumpur City Centre and is currently recognized as the second tallest building in the world, with a height of approximately 678.9 meters and 180 stories. The project was developed by PNB Merdeka Ventures Seri and constructed through a joint venture between Samsung C&T Corporation and UiTM Construction Seri. Construction began in 2016 and was complete in 2023. Beside all the super tall tower, the development also include office spaces, a luxury hotel, retail areas and an observation deck. One of the most challenging aspects of this project was the construction of its multi-level basement, since the excavation extended below the natural groundwater table and was carried out in a densely populated urban area. Effective groundwater control was essential to prevent water ingress, maintain excavation stability, and protect nearby buildings and underground utilities. Next, I will explain the site and groundwater conditions that made this project particularly challenging. One of the greatest challenges during the basement construction of Merdeka 118 was groundwater management. Since the excavation was carried out below the natural groundwater table, groundwater continuously entered the excavation area, making it difficult to maintain dry and safe working conditions. Besides groundwater seepage, the project also faced risks such as ground settlement and hydrostatic pressure acting on the retaining structure. If these issues were not properly controlled, they could affect excavation stability and potentially damage nearby buildings, roads and utilities. Another challenge was Kuala Lumpur's tropical climate, which is heavy rainfall, increased groundwater recharge, and surface water infiltration, requiring the dewatering system to operate continuously throughout the construction period. This groundwater-related problem also increased construction costs due to additional pumping, monitoring, and maintenance requirement. Therefore, an effective groundwater control strategy was essential to ensure both safety and project progress. Move on, I will now pass the floor to Amirul to explain the groundwater control and dewatering method used to overcome this challenge.
Thank you, Hanif. So I will continue to explain groundwater or dewatering method. Groundwater control at Merdeka 118. The project team employed an integrated strategy combining physical barrier with active water removal. For example, like diaphragm wall with 800 mm thickness, this serves as both a structural retaining system and low permeability vertical barrier. By enclosing the site with interlocking concrete panels, the project significantly reduced the horizontal inflow of groundwater from the surrounding urban area. Next is continuous pumping system. Despite the diaphragm wall, water still seeps through the base or joints. A network of submersible pumps was used to continuously remove this water, keeping the table depressed below the active excavation floor. Lastly, deep piling support. The foundation design include 137 reinforced concrete deep piles with 2.2-meter diameter to ensure the superstructure weight was safely transferred through the variable soil into stable strata even while the surrounding ground was being dewatered. Let's continue to discuss the material, equipment, and machinery. To begin, several key pieces of equipment were essential for maintaining a safe and dry excavation site. The submersible pump was used to continuously remove groundwater from the excavation area, while the dewatering pipes transferred the collected water to designated discharge point. A diaphragm wall serves as a retaining structure to also minimize groundwater inflow into the excavation to monitor groundwater condition throughout the project. Piezometers were installed to measure groundwater level. In addition, settlement breakers were placed around the site to detect any ground movement or settlement caused by excavation and dewatering activity. Lastly, generator provide backup power to ensure that pumping operation continue without interruption even during power outage. So let's continue to groundwater monitoring and testing. Ground level monitoring. Groundwater level are continuously monitored using instruments such as piezometers to ensure the water table remain within safe limits during excavation. This helps engineers evaluate whether the dewatering system is effectively controlling groundwater and it identify any abnormal change early. Next, settlement monitoring. Settlement monitoring measure any movement or sinking of the ground around the excavation site. The data helps protect nearby building, road, and underground utility by allowing engineer to take corrective action if excessive settlement is detected. Next is pump performance inspection. The watering pumps are regularly inspected to ensure they are operating effectively and continuously. Engineers check the pumping capacity, flow rate, and overall condition of the pumps to prevent equipment failure that could lead to flooding or construction delay. Lastly, visual site inspection. Engineer and site supervisor carry out regular visual inspection of the excavation area to identify signs of water seepage, crack, soil movement, or any unstable condition. This inspection provides an additional layer of safety and help ensure that any potential problem are addressed immediately. Next, I discuss the cost consideration involved in implementing the groundwater control system. The first major cost was the cost of pumps. Since groundwater had to be removed continuously throughout the excavation, submersible pumps were essential. The project budget included not only the purchase and installation of these pumps but also their replacement whenever necessary due to wear or unexpected failure. Another significant expense was electricity because the pumps operate almost continuously during the excavation period. They consume a considerable amount of power. As a result, electricity became one of the largest operating costs of the dewatering system. The project also includes monitoring costs. Instruments such as piezometers and settlement makers had to be installed and inspected regularly. Engineers also analyzed the collected data to ensure that groundwater level and ground settlement remain within safe limits throughout construction. In addition, there were maintenance costs. Pump dewatering pipe generator and monitoring equipment required routine maintenance and occasional repair to keep the system operating efficiently and to avoid unexpected breakdown that could interrupt construction. Although these costs were significant, the groundwater control system provides substantial long-term benefits. It helped prevent flooding, excessive ground settlement, equipment damage, and excavation failure. By reducing this risk, the project avoided costly delay, protected nearby structure, and minimized expensive repair works. Moving on to the solution implemented, we address several major challenges during construction. For the high groundwater level, a continuous dewatering system was operated to keep the excavation dry and stable. To control groundwater seepage, we combined the diaphragma wall with the pumping system to effectively reduce water inflow. To prevent excessive ground settlement, we carry out regular settlement and groundwater monitoring, allowing us to identify any changes early and respond immediately. During period of heavy rainfall, continuous pumping was supported by proper surface drainage management to prevent water accumulation within the excavation. Finally, to ensure excavation safety, regular inspection and maintenance of the entire groundwater control system were conducted throughout the project.
Thank you, Amirul Hakim. Now we move to the next one, which is chapter 4 that discuss the Tun Razak Exchange, which is TRS infrastructure works and the groundwater management challenge faced during its constructions. First, let me introduce the project. Tun Razak Exchange, or well known as TRX, is Malaysian first international financial district. It is located in the center of Kuala Lumpur and covers about 70 acres. The development includes office buildings, roads, underground utility tunnels, public facilities, and several basement levels. Because of this underground structure, deep excavation was required before construction could begin. However, the construction was very challenging because the site had limestone ground and a high groundwater table. During excavation, groundwater could easily enter the excavation area, which making the ground unstable. To overcome these challenges, the project team carry out several groundwater control measures. They monitor groundwater movement, seal cracks in the limestone using grouting, strengthen the soil, and continuously monitor the site. This measure helped to control groundwater and protected nearby buildings and infrastructure. Now, let's look at the organization involved in this project. The project is called Tun Razak Exchange Infrastructure Works that located in Kuala Lumpur. The client and master developer was TRX City Sdn Berhad, which managed the overall development. The lead engineering consultant was EDP Consulting Group Sdn Berhad, which they were responsible for engineering design, groundwater studies, retaining system, grouting works, and site monitoring. The main infrastructure contractor was WCT Berhad, which they carry out earthwork, road construction, utility installation, and others infrastructure work. This organization worked together to ensure the project was completed safely and that groundwater was properly controlled throughout the construction process. Now we move on to the site and water conditions. The Exchange 109 project at TRX was built on Kuala Lumpur limestone, which contains many cracks and underground cavities. Combined with a high groundwater table, excavation become very challenging due to the risk of flooding, groundwater settlement, and sinkholes. To overcome these issues, engineering carry out pumping tests, seal limestone cracks by using fissure grouting, strengthen weak ground with compaction grouting, and install retaining system and continuously monitor ground movement throughout constructions. After that, I will explain about groundwater problem encountered. Groundwater management was one of the biggest challenges at the TRS project because of the site had a high groundwater table and karstic limestone with many cavities and cracks. These conditions increase the risk of water entering the excavation, ground settlement, and damage to nearby buildings. To minimize these risks, engineers conducted pumping tests, controlled groundwater levels, filled underground cavities through grouting, and continuously stabilized the ground during constructions. Next, I will pass these presentations to Muhammad Atif.
So for the next part, I will explain about the groundwater control method that used in the TRX infrastructure project. Groundwater control was very important because the project was built in Kuala Lumpur limestone formation where the groundwater level was high and the ground conditions were challenging. Before excavation started, engineers carried out site pumping studies and groundwater drawdown assessment to understand how lowering the groundwater level would affect nearby buildings and infrastructure. Several groundwater control methods were then implemented, including retaining systems, fissure grouting, and compaction grouting. These methods reduce groundwater ingress, improve excavation stability, and protect the surrounding structure throughout the construction process. For the next part is the materials, equipment, and machinery that used for groundwater control. The TRX project used different equipment to ensure that the deep excavation was carried out safely and effectively. Pumping systems were used to control groundwater drawdown, while grouting pumps and cement grout were used to seal the limestone fissures and underground cavities. Second pile walls and ground anchors provided support to the excavation, while monitoring instruments such as piezometers, inclinometers, and settlement markers continuously measured groundwater levels and ground movement. Selecting the right equipment and maintaining it throughout construction helps to ensure that the groundwater control remain effective and that nearby structures stay safe. Groundwater monitoring and testing play an important role throughout the TRS project. Engineers continuously monitor the groundwater levels and the ground movement and the performance of the groundwater control system to make sure excavation remains safe. This allowed them to quickly identify any unusual conditions before they became serious problems. Several monitoring instruments were used, just like I mentioned earlier, including piezometers to measure the groundwater levels, inclinometers to monitor the lateral ground movement, and settlement markers to detect any surface settlement. Continuous monitoring helps minimize the risk to nearby buildings, underground utilities, and ensure that the project met its design's requirements. This slide shows the effectiveness and cost implementation of the groundwater controls measure. The groundwater control system successfully reduced groundwater ingress, improved excavation stability, and minimize groundwater movement in the difficult limestone formation. As a result, the excavation was carried out more safely while protecting the nearby buildings and underground infrastructure. Although additional costs were required for pumping studies, grouting works, instrumentation, and continuous monitoring, these investments significantly reduced the risk of excavation failure, excessive settlement, and construction delays. Overall, the benefit of groundwater control outweigh the additional costs and contribute to the successful completion of the project. In summary, this chapter discussed how groundwater was successfully managed during the TRX infrastructure project. The project faced significant challenges due to high groundwater levels and the Kuala Lumpur limestone formation. To overcome these challenges, engineers carried out groundwater assessment, pumping system, retaining system, grouting works, and continuous monitoring throughout the construction. These measures improve excavation stability, reduce groundwater ingress, protect nearby buildings and underground utilities, and ensure the project was complete safely. The findings from this case study will also serve as useful comparison with the groundwater control practices that used in the Merdeka 118 project, which will be discussed in the next slide.
Good day, everyone. It's me again. Now I will present chapter 5, which is the comparative analysis between the Merdeka 118 project and the Tun Razak Exchange or TRS infrastructure project. The purpose for this comparison is to analyze for both project managed groundwater during the deep excavations works, although both projects are located in Kuala Lumpur and involve deep basement construction. They have different geological conditions and groundwater challenges. In this comparison, we focus on four main aspects, which are the site conditions and geological characteristics, groundwater problems, groundwater control, and dewatering methods. And finally, the overall effectiveness and project outcomes. First, let's look at the site conditions and geological characteristics. Both Merdeka 118 and TRS are located in densely developed urban areas in Kuala Lumpur. Because of this, both projects had to protect nearby buildings, roads, and underground utilities during excavation. Before construction started, detailed geotechnical investigations were carried out to understand the soil and groundwater conditions. However, the geological conditions are different. Merdeka 118 consists mainly of variable soil and weathered rock with a high groundwater table. Therefore, the main engineering concern was maintaining excavation stability and controlling groundwater seepage. On the other hand, the TRX project is located on the Kuala Lumpur limestone formation, which contains scarce features such as limestone cavities and fissures. These conditions make groundwater flow more unpredictable and increase the risk of ground settlement. Because of this, TRS require additional ground improvement works before excavation. Overall, although both projects had similar urban environments, TRX faced more complex geological challenges. Next, we compare the groundwater problems faced by both projects. Both projects experience several common issues, including a high groundwater table, groundwater seepage, hydrostatic pressure, and the risk of ground settlement. These problems could affect excavation stability and potentially damage nearby structures if not properly controlled. For Merdeka 118, the main challenge was preventing groundwater from entering the deep basement excavation while maintaining a stable and safe working environment. In contrast, TRX had additional challenges because of the limestone geology. The presence of cavities, fissures, and complex groundwater pathways made groundwater behavior difficult to predict. As a result, groundwater management at TRX was much more complicated and require additional engineering solutions before excavation could begin. Now let's compare the groundwater control method used in both projects. Both projects use similar basic groundwater control methods, including dewatering system, continuous pumping, retaining structures, and continuous groundwater monitoring. These methods help reduce groundwater inflow and maintain excavation stability. However, the TRX project adopted several additional techniques. These included groundwater drawdown assessment, site pumping studies, fissure grouting, and compaction grouting. These methods were necessary because of the limestone cavities and cracks, which allowed the groundwater to flow unpredictably. Meanwhile, Merdeka 118 mainly relied on dewatering system together with retaining structures and continuous monitoring to keep the excavation dry and stable throughout the whole construction. This shows that the groundwater control strategy depends greatly on the geological conditions of the project site. Finally, we look at the overall effectiveness of both projects. For Merdeka 118, the groundwater control system successfully maintained excavation stability, reduced construction delays, and protected nearby buildings through effective dewatering and continuous monitoring. So for the TRX project, although the groundwater control system required higher costs due to additional investigations, grouting works, and monitoring equipment, it successfully reduced groundwater ingress, minimized ground settlement, and improved excavation safety. In conclusion, both projects successfully managed groundwater according to their site conditions. Merdeka 118 used a simpler groundwater management approach that focused on dewatering and monitoring, while TRS required a more comprehensive groundwater control strategy because of its challenging limestone geology. Thank you. That is all from me.
Thank you everyone for your time and attention. We hope our presentation has helped you better understand the importance of groundwater control in construction projects. We also hope that the knowledge we share today will be useful for your future study and career. Thank you and have a wonderful day.